So to summarize, sample mean is random. We don't know, it varies between each sample. And the sample mean, remember, it's a random variable. We're trying to see how those sample means are oriented after you take many samples, how that distribution looks like. This is the derivation, is also called standard error. You'll see standard error, or you can also call it standard deviation of the sample mean. Fun fact is, this becomes normal, so no matter what distribution you start with, if you analyze its, let's say this graph here, if this is the original, and you take a lot of values, so that's sample 1, you take its mean, you plot it here, you take like 20 points, sample it, plot its mean over here, do the same thing a number of times, you'll notice that it starts to form a normal distribution no matter what. In the original distribution, you have a lot of randomness, there is spread, but when you take an average, you kind of diminish the effect of the spread, you cancel it out, and the means will be closer because you're minimizing the noise in the population. Okay, so first question here. Got mass of recycled clay, and we know what its population distribution is. But let me just tell you, this doesn't happen all the time, obviously. The whole point of statistics is to infer. So here, luckily, we got the population. So what's the mean of this sample? Or it's just, sometimes you might have to use sample, like the data you get from the sample. If you don't, if they give you population, then you use a population. And because this is made on the assumption that the sample mean and standard deviation matches a population. Find the standard deviation of x bar. So remember, x bar is the distribution of the sample means. So if you want to find its standard deviation, it will just be sigma divided by root n. So it'll be 6 divided by root of 9. So that would just be 6 divided by 3. It'll be just 2 kilograms. So that's what our distribution looks like. Just to get a picture, our original distribution was normally distributed around 40, and its standard deviation, okay, we have 46 and we have 34. So one standard deviation. That was our original. And then after we took the sample, the distribution of the sample mean, notice the mean didn't change, but it got a bit tighter like this. So standard deviation is now only 2. So most of the data gets clumped up. So one thing I should mention is there is a way to consider, I guess, how many samples you need. So here they took 9, right? There is a condition that you should take 30 or more samples for normality to apply. You might have already done this in methods. Specialist, we check if the sample size is greater than 30, then we can assume normality holds. We can use this distribution. We can say that this is normally distributed. But this condition only holds if the population distribution is not normal. So that means if your original was normal, this condition doesn't apply, so it doesn't matter what n is, because you can think of it like, if it's normal, then if you take a sample, then there's not much, I guess, spread, there's not much noise, so you don't have to take a high number of samples to reduce that noise and get a normal distribution. But if you have something like, let's say, bimodal, something like this, and you take, I don't know, 20 samples, it won't look good. Like your data will probably look like this, I don't know, but it's not normal. It's a kind of rule of thumb that you take above 30. Okay, this is linked to the previous question, but we've got a sample mean of 9 days has this distribution. So remember, this is the sample mean, and before we calculated x bar was 40 and standard deviation was 2, but then normally you write this as the variance, so that's why it's squared. Between what two values do the middle 95% of possible means lie? This rule, I'm sure you've covered in methods. This is the percentage for 1 standard deviation, 2, and 3. And since our standard deviation is 2, this is 2, this is 2, that means 44 is 2 standard deviations away from the mean. All of this will be 95%. Then the remaining 2 tables will be combined 5%, so then it will be 2.5% for the probability that the sample mean is above 44. As statisticians, we found the mean. The mean was x bar, and its standard deviation was this. I prefer to use this notation on textbooks or some exams, or your teachers might say just S. We want to know how good this approximation is. Remember, we took this from a random sample, right? We don't know if our sampling methods were accurate. So we need to know like a confidence level, like how good are these estimates? Because we know the value that we get, the single mean that we get, it's not going to be accurate. There's going to be some room for error to make. And that's why we introduce the concept of a confidence interval. So this is your mean. It's in the middle. So you have your estimates, and then you have this error on each side. Now, what is this error? In physics and chemistry, it was just your uncertainty. It really depends on how confident we want to be. Do we want to be 50% confident? Do we want to be 95% confident? Do we want to be 100? 100 is impossible, but let's say we want to be 95% confident. That means if we repeat this entire process again, then 95% of all the confidence intervals will contain the true mean. The formula is Z, which is your Z score. So this Z is based off the confidence interval. So if we want to be confident that 95% of all the values are covered, this will correspond to a Z score of 2 in Tech 3. If you use a calculator, it will be 1.96. If we want to be more confident, well, this stretches the central tail out towards the ends. So that means as our confidence increases, our Z value increases. That means we need to allow a larger margin of error to be more confident, because if it was a tiny confidence interval, then it probably wouldn't contain the mean most of the time. So Z is proportional to E, or the other way around, sorry. E is proportional to Z, and E is just the error. And E represents 1/2 of this interval. We multiply S on root n. You'll see S. What does this S mean? That's just your standard deviation of the sample. It's symmetric, so that means X is in the middle, your mean, and then you have the error on both sides. So when questions talk about the full width of your interval, this is 2E, and other names, they go by margin of error. This is also your standard error. So I'll just quickly go through what we did. Okay, E, as we said earlier, it was Z times S on root n. Oh, it says use 1.96. Okay, I'll use 1.96. Identify how many samples were taken. It's just one. It's always one, and it will be. So that means we're referring to the sample and not the distribution of the sample. Those two are different things. 9 on root 36, right? And then you just plug it into your calc. You get 2.94. Okay, so we got the margin of error. Now we have to state the confidence interval. So that would just be your sample mean plus or minus the error, because the error can be above the mean or it can be below the mean. We express it in bracket notation. So it will be x minus e and x plus e. It's 24. So this, and it will be 24 plus 2.94, 21.06, 26.94. Great, so that's our confidence interval. What does this mean? It means if we repeat this a lot of times, 95% of the time, the confidence interval will contain mu. So mu will be within this interval. So we can expect that 5% of the time, the real population mean will lie outside of this interval. You can determine whether, like, some questions will be, make a claim, is this claim accurate? Is it kind of like reasonable in this thing? But you can just say, if the mean is outside this interval, then it's not reasonable. The reason we use 1.96 here is because in Tech 3, according to this rule, we approximate a 95% as being a Z score of 2. But this is an approximation because in Tech 3, we don't want decimals. But if you use your calculator, so I'm using the Casio FX CG50 AU. And if we go to statistics and distribution, then normal, if you go to inverse normal, and if you put in 0.95 as the area, you get a z-score of actually 1.96. So in tech active, use this number, tech free, use z equals 2. So yeah, the main takeaway is like differentiate between the actual sample. So if it's just one sample, then great, you get mean, and you also get your sample standard deviation, and then the distribution. If you see x bar, that's what it is, then it'll be like this. Okay, we've got margin of error once again. Show that to halve the margin of error, the sample size must be increased by a factor of 4. It all comes down to this equation, and we want to find the relationship between error, so this thing on the left hand side, and what happens when we increase the sample size. If n gets multiplied by a factor of 4, it's on the denominator, so that means root n gets multiplied by a factor of 2. Proper way you can show this is e is proportional to 1 on root n. So I'll just give an intuitive reasoning. So root n only doubles. That means 1 on root n halves. That means the error halves. Right, this time we've got 2 different random samples. They're both 95% confidence intervals. So what does a sample mean? Well, we know that each interval at its center is the mean. So that means x bar of p will be the average of both endpoints. X, q, it will be this as well. So this will be 52 for this one. This is also 52. Okay, it says sample q's interval is narrower than sample p's, and using error, give 2 possible reasons why. Okay. So we have 3 factors that can affect the error, which is your z-score, which is representing your level of confidence. Then you have S, your standard deviation of the sample. Then you have N, which is your sample size. But we know Z is fixed because we got a 95% confidence interval, so it can't be that. So that means either the standard deviation of the sample was lower, so that reduces the margin of error, or we could also have that the number of samples was higher. And also important thing to know is that let's say you have a confidence interval AB, then your mean is just the average of those 2 points, and the error is just b minus a divided by 2, since error is just half the width. Sometimes they tell you what the width is. You have to be careful. To find the error, you just divide that by 2. Explain what the phrase 95% confident means here. Is it correct to say there is a 95% probability that mu lies in that interval? I would say this is poor wording. It's not really probability. It just means that 95% of the confidence interval will contain mu. You might say that does translate to probability, but the proper answer here is, if you repeat this a lot of times, that's what is expected. It's not the probability, but what is expected. That will be it for today.